Okay, welcome to class. Happy Wednesday. Okay, a couple quick announcements. Homework is due. Go ahead and get that turned into this box there. In the future, make sure you have it stapled ahead of time. If you don't have a stapler, write your name and UID on every page, and we'll do our best to put them together, but it's really better if you can bring a stapler, bring it stapled already. A few people have mentioned they had a hard time finding the homework. It will always be in the Canvas page for the course website, under the Files section, under a homework folder, right? So if you go to Files, a homework folder, you should be able to find it there. There was one of the questions on the reading quiz, which the right answer wasn't there. It got encoded wrong when we put it up there. So I deleted that question. I've since put the right answer on it, and I've made it available as a review, so you can see the right way to do that problem, but it won't be done for any points. That one we threw out. Okay, that was a mistake. Okay, let's dive into today. Today's learning objectives are as follows. We're going to continue to calculate free energy. We're just about there. We're then going to shift gears and we're going to relate thermodynamics to electrochemistry. We'll talk about oxidized species versus reduced species and show you how to calculate which one does what. And at the end of class, if we have time, we'll get to oxide growth and how we predict what type of oxides will grow. Okay? So the last thing we talked about, the very last thing we said is we said that this overall change in free energy for a reaction, that's delta sub R, that's for reaction, delta sub R, the change of the reaction, it's Gibbs free energy, delta sub RG, that it has two components. It's got the theoretical component as well as the experimental component, right? The theoretical component, we remember, that's just as if it was written on paper. Will gasoline burn when you combine it with oxygen? Yeah, that delta G naught, the theoretical component, is definitely negative, meaning it's spontaneous. But if you have no gasoline or oxygen to start with, meaning what's actually in your reaction vessel, then it's not going to happen, right? And that's the theoretical, or the experimental component, right, shown in red. So in order to calculate the experimental component, you have to have something called the reaction quotient. And what we did last time is we calculated the reaction quotient if everything in your vessel was a gas, right? No solids, no liquids. Then the way that we calculate our reaction quotient is from the partial pressure of each component. And we remember that the partial pressure, I think I've got it written down here. Yeah, the partial pressure is just equal to the fraction of the gas present multiplied by the total pressure. So maybe this is a good place to do our first clicker quiz of the day. And this one is for participation only. It doesn't matter if you get the right answer. But what do you guys think? What is air composed of, right? We know that in this room, we're somewhere around 1 atmosphere. We're probably less because we're high in the mountains here, right? So it's not quite 1 atm. But in that 1 atmosphere of pressure, what's actually present? A, B, C, or D. So take a shot at this. I'll open it up so you can actually start answering this. What is it that we breathe in every time we breathe? Everybody had a chance to answer? Anybody still login issues? Can I close it? Should I wait a minute? All right, let's wait a minute. While you're answering that, remember partial pressure, P sub A, where A could be component A, that could be oxygen, for example, is going to be the fraction of oxygen multiplied by your total pressure, okay? So if these percentages, basically, assuming 1 atmosphere, we could use these percentages to figure out what's the partial pressure of all the different species of gas in the air that we breathe, okay? I'm going to go ahead and close this. Okay. What do people think? It is, yeah, mostly nitrogen, which is kind of surprising, right? That we live on a planet with like 80% of the air is nitrogen, which our body doesn't use, like when we breathe it in. Only 21% is oxygen, and that's what we're based off of, right? If you saw Interstellar, the blight, right? The blight that they talked about that was ruining all the crops was basically plants evolving to use nitrogen instead of oxygen, or rather, stopping working in the presence of such small amount of oxygen. But yeah, we have about 21% oxygen, mostly nitrogen, and then 1% or less of everything else. So if you wanted to figure out the partial pressure of oxygen, since we're at about 1 atm, We'd multiply that by 0.21, and that would give us the partial pressure of oxygen, which would be about 0.21, right, of 1 atm. So going back up here to our reaction quotient, if your reaction was happening at 1 atmosphere in this room, and it was between these different components, it'd be easy to figure out what PZ, PY, PA, and PB are, right? Now, reaction quotients get a little bit, they're different if it's not gases. Technically, it's more complicated. For this class, it's going to be easier. We're going to simplify it and do a simplification. If, let's say, component A and Y were solids or liquids, so again, if you have A moles, N sub A moles of component A, N sub B moles of component B, reacting with N sub Y moles of component Y, and N sub Z moles of component Z. This time we're going to say that A and Y are either solids or liquids, whereas B and Z are partial pressures. We would rewrite Q as follows. Q becomes, it's still going to be products over reactants, so it's going to be the partial pressure of component Z raised to the number of moles of Z. But now it's going to be the activity of Y raised to the number of moles of Y. Let me fix that. Number of moles of Y. And we're going to do on the bottom, it's going to be the partial pressure of B raised to the number of moles of B multiplied by the activity of, where are we, A, raised to the number of moles of A. And then what makes our life easy is we're going to say that the activity equals 1. For solids and liquids, this is a huge approximation. This isn't real. It's an approximation. When you take thermo, you will learn how to calculate activities, and it's not always 1. For this class, that's a big assumption we're going to make. But it makes it a lot easier, because if those are 1, then we can just ignore those, right? These two terms, 1 raised to any exponent is still just 1, so we can just ignore those two terms. So it makes our life easier, okay? Any questions on the reaction quotient? Nothing? Okay, let's keep going. By the way, where does this expression come from, right? Delta sub Rg equals delta Rg naught plus RT natural log Q, right? We're looking at the change in the free energy, and we know what about free energy? We know that it's equal to V dP minus S dt. We solved that yesterday, that the change in free energy, dG, equals V dP minus S dt. And if you consider a reaction that happens where there's no temperature change, it's isothermal, then dt, that dt term goes away. So we're left with just dG equals VdP minus S dt, but this goes to 0. If there's no change in temperature, that goes to 0. Okay? So then, if we wanted to figure out the change in free energy, we can figure out the following. We could integrate over this. We could take the integral of dG equals the integral of VdP. And using the ideal gas law, which is that the pressure times the volume equals the number of moles times the gas constant times temperature, we could go ahead and rewrite V in terms of P, then take the integral with respect to P, right? So this becomes, I'm just solving for P here, and it's equal to, I'm solving for V in terms of P. It becomes nRT divided by P dP, right? Or in other words, nRT natural log of P when you solve that integral. So that's where that second term comes from, okay? It's just that the integral of, like, these things don't depend on P, so they can come out of the integral, and then you're just left with 1 over P dP. Well, the integral of 1 over x is just natural log x. So that's where this thing comes from, this natural log of P term comes from, okay? Oops, let me give myself some more space. Okay. Okay, so far I think we've got a pretty good handle on free energy. You know that if you start at this level and you do some sort of chemical reaction that ends down at a lower level in terms of Gibbs free energy, then the delta G was negative, and that's a favorable reaction. You're never going to start at a level and go up spontaneously. You'd have to drive that reaction maybe with an electric, a battery or something that you hooked it up to, or something else, right? So if that's the case, we've got delta G equals delta H minus T delta S. Consider the following. what if delta H was less than 0, but delta S was greater than 0? I'm going to jump over to the clickers for this. Oh, I didn't do these. Okay, those aren't a clicker yet. But what would this be? Would delta G be overall negative or positive? Our change in enthalpy is negative, and our change in entropy is positive. Is that an overall positive or negative? Just write it out is what my suggestion to you, right? We can write out that delta H minus T delta S, right? So in this case, delta H is going to be a negative number minus temperature multiplied by a positive number. Will that ever be a positive number? A negative number minus more numbers, it will only be negative. So that will always be spontaneous, right? How about this one? If delta H is positive and we're minusing temperature times a negative number, so in this case, it's an endothermic reaction that decreases the entropy, it decreases the randomness, that will never be positive, right? So for this one, delta G will always be less than 0. But for this one, delta G, there's no way that it's ever going to be less than 0. That will always be positive, right? Because a negative multiplied by a negative, right? It's going to be adding a positive, right? But how about this one? In this case, it's endothermic, so it's positive H minus T, but this time the entropy increases. Or how about this one? It's exothermic, right? Delta H is less than 0, and it's going to be minus T, but the entropy goes down, so that's a negative, right? In these cases, the last two, it completely depends on temperature. In those cases, it's conflicting. Enthalpy and entropy in these last two cases are both arguing for different things. One says the reaction should go forward, one says, hold your horses, it should go backwards. So how do you know which one wins? It's going to depend on temperature. Take a look at this one. You've got a positive number minus a positive number times temperature. So if temperature is low, then that's going to be a non-favorable reaction. But if you heat that thing up at high temperatures, this term becomes overall more negative, since it's minus a positive numbers, than this one. And so that will become favorable. So there's lots of reactions that are like that. They wouldn't go forward at room temperature, but if you heat them up, all of a sudden they become chemically favorable, right? And the other way around on this one. At low temperatures, you'd expect this one to be favorable. Okay? Okay, let's do this example. Okay. What I've given you here is a chemical reaction. You've got sodium, what do they call this, bicarbonate? Or I forget what it's called, NaHCO3, reacting to form NaOH, sodium hydroxide, and CO2. Okay? At a first glance, it'd be hard to guess what this one's doing in terms of enthalpy and entropy. Entropy is easy. You're producing a gas, so entropy is probably favorable. But enthalpy, that's tough to say. Like, how do you say if the bonding is more or less in these two scenarios, right? So instead, what I've given you is I've given you the free energy of formation under standard conditions, right? Delta GF, that's the change in free energy to form these compounds. And the 0 up there means under standard state conditions. 1 atmosphere, 25 degrees Celsius, right? So if those are given, and they're right there, 1, 2, 3, for the 3 compounds here, go ahead and calculate the change in free energy, delta G sub R. I usually put the R between the delta and the G. Same thing though. What's the change in the free energy for this reaction? And again, if you don't remember from last time, we did this with entropy and enthalpy. It also works for free energy. You're just going to take the sum of the products minus the sum of the reactants, and you would multiply that by the number of moles of each species. So go ahead and give that a start. I forgot my calculator. Did you guys bring one? Care if I borrow it? Thanks, Sam. Okay, another few seconds. Get your answers in. What's up? Okay. Will you send me an email on that? Yeah. We'll make sure you get your points. That hasn't happened yet, so we'll see if that keeps happening this semester. Okay, get your answers in. Another 10 seconds. Okay, we're going to wrap this one up. Okay, this one is going to be a positive 77.2 kilojoules. That's what I got. In other words, the change in the free energy from the beginning state to the final state, you had to go up 77.2 kilojoules per mole. It's a pretty big number. That means that this is not going to be favorable because it had to go up, right? So this reaction as written would not be spontaneous. Instead, you could write this reaction the exact opposite way and it would become favorable. That positive 77 would become negative 77 and that would be the driving force for this reaction. Any questions on doing that? Okay, let's keep going. So again, I ended up with delta G equals positive 77.2 kilojoules per mole. And because it's positive, delta G greater than 0, we say that's not spontaneous. Now that doesn't mean it can't happen. We can drive chemical reactions to happen, right? We can apply work on the system, but it's not going to spontaneously happen on its own, okay? How about this one? It says, if the reaction quotient is 1, meaning when you plug in the partial pressures and the activities, all that, Q comes out to be 1. Then it says the natural log of Q equals 0. It says the reaction isn't necessarily in equilibrium, right? That doesn't mean it's in equilibrium. When reactions are in equilibrium, that's when delta Rg, the change in free energy, is 0 for the overall reaction, right? So let's write it like this. If delta Rg equals delta Rg naught plus RT natural log of Q, if you plug in 1 for Q, if it happens to be the case you have 1 for Q, this whole term goes to 0, right? Because natural log of 1 is just equal to 0. But it's delta Rg that we care about. That's the one that dictates whether a reaction goes forward or not. And if delta Rg naught is non-zero, then you're not at equilibrium. Equilibrium is defined at the point at which this term right there is equal to 0. Or in other words, if you set that equal to 0, you could calculate what value of Q, or what temperature, right, would lead to your reaction being at equilibrium. So you might have a case where a reaction will stop if you get to a certain temperature. It will no longer go forward, right? Any questions on this, on equilibrium? We're going to do some examples. Let's start with this one. Okay, the question says the following. You start with a reaction of the same exact thing as before, but this time you have excess CO2 gas. That just means that it's pure CO2 gas, basically. The reaction will reach equilibrium when delta Rg equals 0. That's what we've just been saying. When this equals 0, then there's no driving force for it to go from the beginning to the final state because they're at the same level, right? Where you start and where you end are at the same level, so there's no driving force for it to happen. The question is, what will be the final partial pressure of CO2 in this chamber at equilibrium? So I'll help get you started. We know that normally we'd write delta Rg equals delta Rg naught plus R times T times natural log of Q. Remember that R is our gas constant. That's 8.314 joules per mole, right? And temperature needs to be in Kelvin. Is it joules per mole, Kelvin? I think it is actually. Yeah, it is. Okay, so that's why temperature has to be in Kelvin. Okay, this time we're going to say, okay, at equilibrium, we want to figure out what's the partial pressure of gas in this system. So as soon as we say at equilibrium, you know that this whole side of the equation is going to be set equal to 0. Okay, we're going to use the same delta Rg as we just solved for. That's a positive 77,200 joules per mole. Notice I went ahead and converted that to joules instead of kilojoules because our gas constant is in joules. Doesn't matter which one you do. If you want to work this problem in kilojoules or joules, just make sure that you're consistent. I'm going to convert it to joules, right? This is going to be plus 8.314 joules per mole Kelvin multiplied by temperature. Have I given you a temperature? So this was done at room temperature, so we're going to use 300 K there for temperature. Multiplied by natural log of Q. So what is Q for this reaction? Well, the reaction's right here. That's our reaction. And you notice right away that the first two things, the reactant and the first product are both solids, which means we can just leave them off of our reaction quotient because they're going to be equal to 1. The only thing that we need to consider is CO2 gas. And since it's a product, Q is just going to be equal to the partial pressure of CO2. Okay? We would raise that to an exponent, except the exponent is just 1, so I'm going to leave it off. Julia?
Where did you get the 77,200?
Good question. So we just solved for it right here when we calculated delta RG naught. Yep. We found out it was a positive 77,200 joules per mole. So go ahead and solve for, since we now know that Q is just equal to the partial pressure of CO2, go ahead and solve for the final partial pressure. I think this is our next clicker question. First off, let's answer this question. It says the following. Considering only delta RG naught for what we just solved for, is it spontaneous or not? Remember, it was a positive delta RG naught value. We just talked about this one, so it should be pretty simple. Okay, get your answers in. We're going to move on. It was a positive delta RG naught. Is that spontaneous or not? Okay, I'm going to wrap this one up. Answers in. Okay, while we're waiting a second, what are thoughts on Top Hat? Does it work okay? Does the device work okay? Browser, app? Mostly good? Raise of hands, who's had an issue so far where it didn't work? So a handful maybe? Okay. Okay, I'm going to close this one. Okay, that one definitely, does it go forward? No, it's not spontaneous because it had a positive value. Okay, this is the question that we just set up. Okay, at 298K rather than 300, it's not going to change your answer very much. What will be our partial pressure of CO2 at the end? So go ahead and work this one out. Again, that's how you set the problem up. I'll write down what the options were right here. Is it a very high partial pressure or a very low partial pressure for this thing to be at equilibrium? What's up?
Will you just go over why, kind of re-go over why partial pressure doesn't have an exponent?
Okay, so it does have an exponent, but if you look at the chemical reaction, it's 1 mole of NaHCO3 yields 1 mole of NaOH and 1 mole of CO2. So the coefficient in front of CO2 is just 1. Therefore, that becomes the exponent. That's why I've left it off. If we wanted to be complete, you could put 1 there, but it's just the same. Any other questions? Never sure how long to wait on these. Like, it seems simple, but maybe more time is better than less.
Do you usually get 100 kids
Oh yeah, better than 90%, the vast majority submit. Here they just solve for Q. So the one thing that they may not remember is that you take e to both sides to get rid of the natural log. Maybe they've forgotten that from algebra, but otherwise it's a straightforward question. Okay, another minute. This should be a pretty simple calculation. Okay, I'm going to go ahead and wrap this one up. Well, get your final answers in, but one way to think about the answer to this question without even doing the calculation is as follows. We know that it's not spontaneous, right? And the reaction as written is up there, NaHCO3, NaOH, right? If it's not spontaneous, right, then do you think under equilibrium that you're going to have a really high partial pressure of products, meaning it's gone forward, or a really low partial pressure of products, right, is another way to think of it. Because that's the two options, really big number or a really small number. Okay, I'm going to go ahead and close this one. People think, good, yeah. Very, very small numbers, what should be correct there. If you ever have questions on these, you can always shoot me or the TAs an email, and we're happy to walk through these with you, okay? If you want to see more examples of these, I've done a bunch more right here, and at the end of the chapter, if we have time, we're going to do more, but you can follow these on YouTube. They're worked out in all their gory detail. Yeah?
What about if CO2 is in reactants? What Q will be?
Okay. If, let's say we wrote that reaction the other way, that it was CO2 and NaOH reacting to form the other way, when you write the reaction quotient, it's always products over reactants. So in that case, it would be 1 over the partial pressure of CO2. Yeah, good question. Okay? Okay, let's shift gears. Now we're going to rejoin the book, chapter 16. I told you, like thermo is like, we did like a really mild introduction to thermo, right? Now, chapter 16, we're not even going to read the whole chapter. We're going to read 3 sections, which is about half of the chapter. Section 16.1, 16.2, and then we'll jump ahead and do 16.10. We're going to skip all the rest of it, okay? And there is one mistake in the book. Equation 16.17 should be as follows. It's got a typo in the book, okay? Now, why do we introduce this now? Because free energy and electrochemistry are surprisingly, I think even shockingly related, right? They're like so similar. What is electrochemistry? Electrochemistry is this. It's a reaction where you have both an oxidation and a reduction, and there's typically either a voltage driving this or a voltage that's spontaneously produced. So take, for example, this one. In this picture, you have a zinc anode. We'll talk about anodes and cathodes in a minute. On this side, you've got a hydrogen cathode, right? So you've got zinc ions that are, there's an equilibrium between zinc dissolving and zinc ions replating, right? There's some equilibrium process, some of them dissolve, some rejoin, okay? And meanwhile over here, you would have an equilibrium between hydrogen ions combining to form H2 gas and vice versa. But if you hook these two things up, what you'll see is that electrons will depart from zinc and travel through the circuit. They'll come over here. That electron, which left from zinc, will react with the hydrogen species to form H2 gas, right? So here's the process. You have zinc giving up 2 electrons to form zinc 2 plus. And on the other side, if you add 2 electrons, that should be on the other side. That's just bad, whoever made that drawing. The electrons should be adding up with your hydrogen ions to form H2, okay? Or in other words, in this exact couple between hydrogen gas and zinc, the zinc metal gets dissolved, the metal actually turns into ions, and your hydrogen gas naturally bubbles up, and this happens totally spontaneously, right? So we could write down the oxidation and reduction reactions. They're included right there. You know, that one's messed up, the one on the right. But the oxidation, that's the one that loses electrons. Which one loses electrons? Yeah, zinc. Zinc loses electrons to become zinc 2 plus 2 electrons. And then the reduction reaction is one that gains electrons. That's going to be H plus, right? Picks up an electron to form a half of an H2 molecule. Okay? That's your reduction and oxidation. So this will be oxidation, or it was oxidized. This was reduced. the oxidation occurs at the anode, and the reduction occurs at the cathode. That's just the convention of these, right? So think of whatever name you want. Put them on your note sheets to remember those. But the oxidation, the loss of electrons, happens at the anode, and the gain of electrons is happening at the cathode. Okay? Okay, let's do a demo. Our TAs are awesome, and they've built a sweet demo for us. So you may not know this, but before 1982, I think, or 3, somewhere right around there, the United States was silly enough that when we made pennies, it was pure copper. Even though, like, if you take the mass of a penny, multiplied by the amount of copper in there, right, and then the price per copper, it's worth more than a penny to make a penny. Like, that's just like federal government doing federal government things, right? Which is crazy. So they wised up a little bit. I still think it's more expensive, but it's not as bad. But they place on the inside of the penny zinc now, and then they just plate the penny with copper, right? Make sense? So imagine this. What if you have copper and zinc connected electronically? Will one get oxidized and one get reduced spontaneously? Or in other words, if I take these two things, this is say copper and that's zinc, and I connect them with a wire, and I put a salt bridge between there, and I'll describe what all that does in a minute, will one of them get plated on, like the stuff that was in solution is going to plate onto the surface, and the other one's going to dissolve away spontaneously? Yeah, that is going to happen. So let's show them this demo. Maybe you want to put it up on that table. What we've done is right now, if you take a penny, it's completely encased in copper, right? So if you stack them together, if you connect them, the zinc is isolated, right? What you need is to definitely not deface currency and polish off one side. But if you did, you could imagine that now you've got copper on one side with a zinc junction. Then you put a salt bridge. We'll talk about what that does in a minute. It's just a piece of filter paper soaked in vinegar or salt, right? And you stack these things up. What you'll find is that there's a spontaneous voltage that exists between these. So I'm going to kill the lights. And that's not expected. I'm even going to kill one of these. Let's do the center and turn that one off. Okay. You might be able to see this. I have an LED here. Oh, gosh. Okay, and we've got foil, and we'll see if this works. LEDs only work if you get the voltage one direction. I don't know which one it is, so I'm going to try both ways. But what you hopefully be able to see is if I connect the tin foil, which is just the current collector on the top and bottom of this thing, it should light up. Not that way. All right, Logan, I'm going to have you try and fix this. I broke your demo. All right, Logan's going to try and fix that. What should happen, though, is that for an LED to work, there's a critical... Oh, there you go. You guys see that? So we are lighting up an LED with just pennies, right? There's no battery hidden inside here. We went full Breaking Bad on this thing, and now we have an LED that lights up. Okay, thanks, Logan. So how do you do this, right? What's actually going on here? Every time that you put one of these together, it does produce a spontaneous voltage, right? That's the exact same as saying it had a negative delta G, like the reaction happened spontaneously. Now, each one of those pennies, if you put them together, it doesn't produce enough of a voltage. It doesn't produce enough of a voltage to light up the LED. The LED, a red LED, takes, I think, something like 2 electron volts. And so you have, or 2 volts, I mean. And so you have to stack up 5 or 6 of these things to get enough voltage. But if you stack them in series, then you can just add them right up, right? So let's go through the reaction, right? Consider if you had a couple of iron and copper, right? So in like solutions like that, in one case you've got iron and copper, you connect them, you're going to find that the iron gets dissolved, right? But if you take iron and zinc, no longer copper, this time the zinc gets dissolved. So what's the difference? How do we know which one will be dissolved and which one's going to get plated? Because here we had 2 examples where iron's in both of them, and in one case it's the one that's dissolved, in the other case it's the other one. You have to have what's called a standard reduction potential to figure it out. Here's the standard reduction potential from our book, right? So it's a table of reduction reactions. In all of these, it's an ionic species like magnesium 2+, being reduced, because it's gaining electrons, it's picking up 2 electrons to form magnesium metal, right? And it goes all the way up. And for each one of these, it's going to give you an associated voltage, right? For this one, potassium, to pick up an electron, to become potassium metal, has a very large negative voltage. Meanwhile, very high at the top, gold, 3 plus, picking up 3 electrons to form gold, has a really large positive voltage, right? So the key here is that to have a redox reaction, you can't just have a reduction. You have to have an oxidation as well. So what's going to happen if you put two of these things together, one of them you're going to have to flip the equation. You're going to have to reverse it. Like for example, zinc is going to be on the left-hand side, and zinc 2 plus and 2 electrons will be on the right-hand side. And now we've written an oxidation reaction. So you have to have one of each, one as written and one reversed. And when you combine those together, that will be your total reaction. So let's look at the example that we just saw. Iron and zinc. Let's find them. Okay, iron's right here. Iron 2 plus, picking up 2 electrons to form iron metal. Meanwhile, when it was with zinc, zinc is zinc 2 plus 2 electrons to form zinc. These have different voltages. And I hate that the convention made it this way, but it turns out that a spontaneous electrochemical reaction is one with a positive voltage. So a negative delta G is spontaneous, but a positive voltage is spontaneous, right? So if you were to flip one of these so that it gets oxidized and then add them together, you would want to flip the bottom one because it's more negative than the iron, right? The iron is negative 0.44. The zinc is negative 0.76. So if you flip the zinc so that it's positive 0.76 and you add these things together, you're going to get a positive voltage, right? Positive 0.763 plus, this negative 0.44 is going to give you a positive number, and therefore it's spontaneous. So all I would have to do is give you a table like this on the first midterm, and I could say, if you made a electrochemical cell out of, say, lead and copper, which species gets oxidized? So maybe turn to a neighbor and tell them, which one gets oxidized, lead or copper? Lead's right here, copper's right there. Which one gets oxidized, meaning it loses electrons and gets dissolved? Okay, what do we think? You've got lead and you've got copper. Which one gets oxidized? Anybody feel brave? Okay, remind me your name. Ashton, what do you think? Which one's going to get oxidized? Lead will get oxidized is correct. The reason why is because right now both of those values, lead is negative 0.126, copper is 0.34. The one that's more negative is lead, right? So you're going to flip it, and it becomes a positive number. When you add 0.34 plus now positive 0.126, you get a positive number. That's correct. Okay? If you did it the other way, you're going to end up with a negative number, which tells you that you did it wrong because that's no longer spontaneous. Okay? Yeah, Anthony?
Your logic was setting up to 0.763, and the same thing in this one. So
Okay.
you're taking the lowest.
The one that's more negative, the one that's lower on the table, you're going to flip it. You're going to write the reaction backwards. We're going to do this in just a second. You literally write zinc over here, zinc 2 plus the 2 electrons over there, and you change the sign, and then you add the two together. This is now a positive number plus a negative 0.44. It becomes an overall positive number. Let's do an example of this, okay? So let's do iron and zinc, right? Iron, 2 plus 2 electrons is going to form iron metal. And that voltage, the standard reduction potential, we could take it from the table, but that's equal to negative 0.44 volts. Let me make that a little thicker so it's easier to read. Meanwhile, we've got zinc, 2 plus 2 electrons forming zinc metal, and that reduction potential is equal to negative 0.763 volts. We take the one that's more negative and we're going to flip it. We're going to rewrite this. We're going to say that zinc is now reacting to form zinc 2 plus 2 electrons, and our voltage gets reversed. It's now positive 0.763 volts. We can go ahead and get rid of this one, scratch it out. Now you're going to combine those two together. Let's write our overall redox reaction. By combining the reduction and oxidation half-cell reactions, we can get the overall redox reaction, right? And it's going to be as follows. It's going to be zinc plus iron 2 plus ions gives us, plus 2 electrons, gives us zinc 2 plus iron metal plus 2 electrons. So the electrons cancel out on each side. So sometimes people don't write the electrons because they cancel out. But it's important to realize that they're happening, right? One species is giving up electrons, the other one's picking up those electrons. And the voltage for this, the delta V naught, we call it, is going to be equal to negative 0.44 volts plus 0.763 volts. When you add those together, it comes out to be positive 0.323 volts. Since we end up with a positive voltage, this would be a spontaneous reaction. So you could say with confidence that the zinc is the one that's going to dissolve and iron is going to get plated onto here. Okay? Other questions? Yeah, Thomas?
Because of the ionization energy is less for the zinc than it is for the other, right?
Yeah, it's not the ionization energy. It's called the standard reduction potential. But yeah, it's the voltage associated with this electrochemical half reaction. Okay? We've got lots of examples of this, right? There's big tables that basically show you a lot of this stuff. So for example, it's in this table, it shows you right here. So it shows you when you bring different things together. If you took, let's say, copper, and you combined it with titanium, you come down there and it's that number 230. That number is green, and so green says this contact is practically neutral, meaning it doesn't produce a very big voltage one way or another. But take this one. What if you combined copper with platinum? Then you get a 570 and it's blue. Blue means the metal of the abscissa, or that top row, gets attacked. So if I combined copper and platinum electrochemically, then the copper is going to get corroded, right? Meanwhile, over here, red means that the side row will. So if I combine bronze with, say, steel, if I weld bronze and steel together and let it do its thing and corrode, I'm going to find that the bronze corrodes instead of the steel, right? So these tables are really handy. They're called galvanic series. There's one in the book, and we're going to talk about them a little bit more on the next homework. Yeah, Anthony?
So is any of these metals combined, if they have a spontaneous whatever, are you going to do something similar to what the battery did?
Absolutely. Yeah, it's going to produce a voltage, right? And it's going to corrode. So anybody ever heard of a sacrificial anode before? Anybody heard of this? Anybody replaced a water heater in your home? Anybody own a home? If not, there's something to look forward to. Replacing water heaters, right? Water heaters have a sacrificial anode on them, which is a material which intentionally is connected electrically to the rest of your big tank. Your tank's probably steel or something. But you put a sacrificial anode on there such that it gets corroded rather than the steel, right? So let's go back over here. If we go to our standard reduction table, steel is not listed, but there is iron. Let's say that steel behaves a little bit like iron. What material of the ones on this table would you use for a sacrificial anode? Meaning you want it to corrode and not the steel. Because it's okay if a little bar of sacrificial anode corrodes. It's not okay if 100 gallons of boiling water corrodes. That's not a good thing, right? If the steel holding the water corrodes. Okay? What would you use? Of the ones listed here, what would you use for your anode? Yeah, Ashton.
Aluminum or zinc.
Those would be great options. Aluminum, zinc, magnesium, they use these things all the time for sacrificial anodes. They're things that are further down on this chart, meaning they are already more reactive. They're going to tend to, they're going to tend to give up electrons more than these other things will, right? That's a sacrificial anode. You can put those on boats, you can put those on all sorts of things. Wherever you don't want the corrosion to happen, but you don't care if something else corrodes, that's your sacrificial anode, okay? We're going to come back to that. Okay, now just like before, with delta G, the delta RG, that's the change for the reaction of your free energy, that didn't tell the whole story, right? That had two components. It had the experimental and the theoretical component. It's the exact same with electrochemistry. You have to actually include both parts, right? I'm going to jump down to this for right now. What you really care about is delta V, right? Your delta V for the overall reaction. And that's equal to what we just calculated, delta V naught. That's like the theoretical part that we described in free energy calculations. But you also have to consider that part, which is the experimental component, okay? The experimental component, you notice it looks almost the same. Instead of plus RT, natural log of Q, this time it's minus RT over NF. That's just to give it the right units. We used to have units of joules per mole. Now it needs to be units of volts. So we divide by Faraday's constant, and N is the number of electrons. Right? N is our number of electrons. F is the Faraday constant. And then instead of a Q, a reaction quotient, I'm writing it as the concentration of the oxidized species divided by the concentration of the reduced species. Where does this come from? Well, this is our overall equation. Is this blue? Yeah, blue. Let me write this thing. That's our equation, right? Whenever we write the reaction quotient, it's always products over reactants. In this case, the oxidized species will always be the product, and the reactant will always be the reduced species, right? Zinc 2 plus over iron 2 plus. Okay, just products over reactants. I think that's easier than trying to remember the formula in the book. The formula in the book gives you like this silly like M1 and M2, and you're never going to remember which one's which. So instead, what I strongly suggest you all do is write out the full electrochemical reaction, and then it's just products over reactants when you figure out what goes in the natural log, right? Q is just products over reactants, okay? Now before, we said liquids and solids, that they don't get a value. We just replace them by 1 when we write the reaction quotient. That's not the case here. Here, we replace Q, when it's dissolved ions and species, we write it as the concentration of the oxidized species divided by the concentration of the reduced species, right? So those are the concentrations. That's typically in something like molar, right? So how many moles per liter? Okay? Any questions on this? We can do some examples, but any questions so far on this? Yeah, Julia.
Can you reiterate why this is not equal to 1 again?
Okay, so in a solid and liquid, those species, the concentration don't matter. It doesn't matter because it's the activity. Here, the concentration very much matters because imagine this for a minute. If you go back to your species that are dissolved, could you bubble hydrogen gas if you didn't have any hydrogen ions in solution to start with? Like that reaction can't happen. And so the concentration of this species is going to dictate the reaction. Same thing over here. Zinc dissolving to zinc 2 plus, you have to have that concentration. So we're out of time. When we pick up class next time, we're going to do some examples of this, and then we'll probably move on to chapter 10 after this.